Hello. So good afternoon, everyone. I'm Zhi-Hua Zhou from Nanjing University, and it's my great pleasure to chair this invited talk session. So it's my great honor to introduce to you our invited speaker. He's Dr. Rong Jin from the Alibaba company. Maybe you know the Alibaba company is the biggest one in e-commerce in China, also one of the biggest in the world. And Rong Jin now is a leader of IDST of Alibaba. IDST is a technology center of the Alibaba company. So Dr. Jin obtained his PhD degree in College Mellon University. And before joining the Alibaba company, he was a professor of the Michigan State University. And Professor Jin's research previously is full of theory. If you look into his papers, they are full of generation bonds and full of other theories. Now he's in the industry, and it will be our great pleasure to see how theoretically elegant approach can be so amazingly well, work very well in industry applications. So please join me to welcome Dr. Rong Jin.
Okay, thanks for coming to my talk. As Zhi-Hua just said, I used to be a theoretical person. So the time I joined Alibaba, actually I'm a strong disbeliever of deep learning. But as things goes on, you see a lot of good performance that been delivered by this machinery that really make me to think really hard about this problem. So today, I would like to tell you some of the interesting development of deep learning technology that we have done in Alibaba. Now, as everybody here probably know what machine learning is about, so the fundamental idea of machine learning is try to learn a target function with a small number of samples. So the key ingredient for most learning framework is composed of three things. One is specify the function space that you aim to learn. The second is to specify the number of instances you have been collected for the training purpose. And finally, you need to find out appropriate and efficient optimization algorithm that allows you to find the best solution among all the candidates that you have using the data. Now, in terms of deep learning, things are slightly different, right? So first of all, whenever you look at the function space for the deep learning, we're mostly looking at so-called a non-smooth recursive function. This kind of family really gives you the power of representation, but at the same time pose the challenge in terms of searching for the final good solution. On the other hand, as we all know that deep learning tends to give you a very complicated categorization of potential function. So typically speaking, you have to collect large enough of training example to narrow down the potential solution. A final challenge coming from deep learning in terms of this empirical risk minimization framework is to do the optimization. So deep learning usually gives you a non-convex optimization that often leads to a very challenging optimization problem. Often it's the case that you don't even know the solution you find is local optimal or not mention that it's a global optimal. So now, before I jump into the discussion about some of the work we've done in Alibaba with respect to using the deep learning technology, I would like to give everybody here a slightly full picture about what Alibaba's business is doing. Now, as many people probably here know that Alibaba is mostly doing the e-commerce. We have done great success on the e-commerce platform. We have Taobao, Tianmao, Zhi-Hua, which is really serving the Chinese users, but we also have American Express, the AE, which is AliExpress, and also the Lazada. Those are the platforms really serve the overseas users. Now, besides the e-commerce platform, we also have a very wide spectrum of business scenarios. I would like to name some of the very important ones. For instance, we have Ant Financial, really focused on the financial data analysis. We have Alibaba focused on the computational advertisement. We have a Weibo, which is one of the largest websites for social media. We have Gaode for the local business service. We have Youku and Tudo, which is one of the largest video websites in China. And we also have a China, which is really focused on developing technology for logistics. So as you can see, the business spectrum of Alibaba is really wide. And that actually gives us a tremendous opportunity to look at the successful application of deep learning technology. So here, I'm simply just categorize a few very important applications of deep learning. So as you can see, we have very successfully applied deep learning to information retrieval related applications such as the search and recommendation system. We also applied deep learning to speech, natural language processing, and video and image analysis. Those applications range from very low-level things like spelling checking to the very high-level things like semantic understanding of the video sequence. Apparently, beyond that, we also have a team devoted to developing the state-of-the-art technology on deep learning, as well as for larger-scale convex and non-convex optimization technology. Those technologies really forms the foundation for us to pushing the agenda on various different applications. Okay. Now, apparently, I have no way to give you all the details about every possible application we have done within Alibaba using the deep learning technology. So here, I'm going to simply looking at a few samples that, at least from my viewpoint, are very interesting. So we're going to talk about a few applications related to computer vision. We're also looking at application of deep learning technology for speech and natural language processing. We also have some discussion over this presentation about how to explore deep learning for combinatorial optimization problem. And then finally, I would like to tell you some of recent progress we have made by using the combinatorial technology for the model compression for the deep learning problems. Okay, so let's first of all looking at computer vision application. So the very first things I would like to mention over here is the image search or visual search. So in Alibaba, we have an application called the Pi Litao. Basic idea is that if you see something interesting, now instead of typing all the related information, which tend to be very expensive, you simply can take a picture of the items of interest, and the system will be able to match that image with one of the items in our repository and then bring you directly to the shopping website of the item. So this really gives users a great experience in terms of identify the items they look for. Now, the challenge of doing this, even though image matching technology has been studied for many years, the particular challenge you're looking at over here is that our repository, our database have over 100 million different items, meaning that each time, whenever you see a picture, you really have to match that picture of item with respect to 1 out of 100 million items in the database. And that by itself is a tremendous challenge that you have to deal with. Okay, so this product has been developed for 3 years in a row, and we actually have over 12 million users that have been using this product on a daily basis. And the whole process of computing the matching between the query image versus the image in the database is pretty complicated, but most of the components will be involving the use of deep learning technology. Apparently, I'm not going to jump into detail about every component within this product, but I do actually want to mention one of the core components, which is called the deep ranking. So basic idea is that we like to take all the log data we have and try to figure out how to compute a appropriate representation of the image to be such that our matching results would be as accurate as possible. So our approach would be based on triplet training. In this case, you take the query image uploaded by the user. You also take the clicked image and together with the non-clicked image. And these 3 images will form the triplet. Your goal is to find the representation to be such that the distance between the query image versus the clicked one is going to be very considerably shorter than the distance between the query image versus the non-clicked one. So as you can see, this is a very conventional way to doing the representation of machine learning, has been existing for many years. Now, the particular computational challenge we have handled in practice is that we have too many possible triplets to deal with. Remember, we have over 50 million image queries being uploaded on a daily basis. So if you think about that you typically have to deal with over 100 billions of triplets. And that is computationally expensive if you have to update your model almost on a regular basis. So the things that we make it work is we take this so-called dynamic construction of triplets, meaning that we basically adding those triplets based on how those triplets being violated by the existing representation. And those challenge triplets is going to be used to update our representation gradually. So in this way, on one hand, we avoid the challenge of having to utilize all the triplets, which is computationally expensive, but on the other hand, we try to keep as much information as possible from all the very useful triplets. Okay, so here are some examples that I'd like to show. So here's the picture of the shoe, and as you can see, the system correctly identified the exactly shoe based on the matching of images. This is another example of the wine. Again, the system is able to identify the wine even though there's an apple around. Finally, this is an example about picture of furniture desk. Again, using the PyTile, we're able to identify the same items from the database based on the matching of images. Okay, so after we have done successful job with PyTile by matching the image of the items, we then take the one step forward to think about if we can take this technology and doing the matching of everything, right? What if I can do the matching of the flowers, of the trees, of buildings, anything that you can think about in the mind. So we call it matching everything. Now, immediate challenge you is going to encounter is that unlike the e-commerce domain, we really have collect tremendous amount of data based on the interaction between the user and the system. For most of the domain we're going to deal with, we no longer have such luxury of using the data coming from the user feedback. So the question is, can we fully leverage the information or data we collect from the e-commerce domain and then export them for the purpose of representing the image in the different domains? Apparently, everybody here would ring the bell. This is a problem exactly addressed by the transfer learning. Okay, so the simplest way to do the transfer learning, as probably most people can immediately come to your mind, is to do the linear transformation. So let's say the X is the representation that you get from the PyTile based on the image data you collect from the e-commerce domain, right? So now, what if I can learn a linear transformation, W, and that transformation while mapping this PyTile representation to the particular domain that you'd be interested. Okay? And this is clearly a feasible and effective approach that we can imagine. But apparently, there's one clear limitation of this approach, which is by no means that transformation from e-commerce domain to the other would be simply categorized by a linear transformation. So how can we do a nonlinear transformation, particularly if I have no idea what exactly would be the right nonlinear transformation in mind, right? So ideally, it would be the case that if I can specify a function space f and I would like to search for all the possible candidates within function space f1 to fm that allowed me to do the best transformation from the e-commerce domain to the one that you would like to have. Okay? So we have a very simple scheme to deal with this problem based on the random Fourier transform. So the idea is the following. So on the very bottom of this stack is the representation coming from the PyTile. Now, instead of directly doing a linear transformation, I'm going to apply a nonlinear random Fourier transformation to get the intermediate layer called x hat. And then on the top of x hat, I will learn a linear transformation that will allow me to map in this X hat to the target domain. Now, I guess people here would wonder, why on earth this nonlinear random Fourier transformation is of any advantage for our purpose? Sorry. Turns out, there's a very well-known theory that tells you that if you restrict yourself for the functions to so-called reproducing Hilbert space endowed with RBF kernel, then these two approaches are exactly equivalent, at least in expectation. So therefore, by using the random Fourier transformation, you actually can explore all the possible nonlinear transformation function within the family of holder class, which is a great. So let me show you some empirical results we have done to verify those approach. So our source domain in this case are the training data from the PyLitau, and our target domain in this particular case are the images from the open image database. So if you simplify a PyLitau feature, and then the accuracy for the top 10 would be only 53%. Now, if you're training a GoogleNet from using the data from the open image, you will get very much the same performance. Now, if you can combine the PyLitau data together with the linear transformation, that will give you additional 4% improvement in terms of accuracy. Now, if you're adding one more point, which is random Fourier transformation, you will get one additional points in accuracy improvements. Okay? Oh, by the way, if you have any questions, you probably can interrupt me, or you can ask by the end of the talk. Now, talking about transformation, there's another interesting thing that we have been working on, seems to be working pretty well, which is called robust optimization. Okay, so the idea is the following. So you have a data, which is called DS, are the data coming from the source domain. You have the data coming from DT coming from the target domain, right? So one way to actually leverage the data from the source domain for the target domain is to search for a prediction function that can yield a good prediction performance on both domains. And one way to characterize that idea is so-called robust optimization approach. In this case, you're searching for the function that is able to minimize the loss, the maximum loss between the target domain and the source domain. So this is the theoretical analysis for the robust optimization is being well established by the work of Miroski and Ben Tao. Now, even though this is a very successful approach, but one issue usually coming to our observation is that even though the source domain have some similarity with the data from the target domain, but often is the case, many of data points coming from the source domain are actually very different from the target domain. So directly comparing the loss function between the source domain and target domain may not be a fair comparison. Now instead, maybe we have to run a selection process. That is to identify a subset of the data from the source domain that bear large similarity with the data from the target domain. So as you can see, if you have that in mind, then your optimization problem have to involve in two decision variables. One is to find the appropriate prediction function. Second is to identify the subset of the data from the source domain we call the DS hat that bury the large similarity with the data from the target domain. So just to give you the very simple illustration as why this is a sensible idea. So consider you have, data DS for the source domain, the data DT from the target domain. Each color identify data points from a different class. Okay, so now if you train if you train a model from DS and then apply directly to the DT, as you can see, the prediction accuracy is very lousy. Now, if you are able to intelligently select subset of data from the source domain and then combine that with your data from the target domain, then you will be very lucky you can get a very high accuracy prediction in this particular scenario. Okay, so we run that idea over the problem of classify if image is a pornograph image or not. So our source domain in this case are the massive amount of data being labeled as a sexual image or not. So we try to leverage that data and to improve our prediction capacity for those, for the image pornograph or not. So as you can see, if I directly using the data from the target domain due to the limited number of training instances, we only get 68% accuracy, but combined it with the data from the source domain, using the robust optimization technology, we're able to improve it to 98%, and then you can push the gender further to over 99% by injecting the approach of selecting of training instance from the source domain. Okay, then I think the next things we try to extend the PyDTAL is to so-called cross-media retrieval. And so the idea is try to matching the text query with the image in your database. And this is actually an important application for Taobao search because in many cases, the seller would upload the items without giving sufficient description of the item, other than they have a very nice pictures. So in these cases, if you simply doing the text-based matching, you are not be able to identify of those items, but you can identify those items by utilizing the capacity of cross-media retrieval. The 3 examples shown over here is just to see that by keep on modifying or specifying your queries, you are getting different results by using the technique of cross-media retrieval. So the overall technology that we developed for the cross-media retrieval is very similar to the one for the PyDTAL. Again, the training is based on Triplet. The key difference is that we are using the texture query as part of Triplet instead of the image query. And other than that, most things are similar. So again, you try to come up with appropriate coding for the text as well as the coding for the images, so that the Triplet will be able to satisfy and with our constraints. Okay, so we did the evaluation of this approach over the Microsoft COCO benchmark. And so we compared a few state-of-the-art technologies. As you can see, the performance of our approach seems to be on par with the best results being delivered over this benchmark. And so we have been working very close with our colleagues from the Search BU, applying this technology to Taobao search, particularly for those queries that tends to retrieve a very small number of items. And we do actually find by utilizing the capacity of cross-media retrieval, we are able to significantly improve the conversion rate for those lousy queries. Okay, so the second component is about the application we have done with respect to the speech and the natural language processing. So pretty much everybody here, knowing that we have observed a very significant improvement in the speech recognition for the last 10 years, for the last 5 years, I guess, mostly due to the application of deep learning and also due to the availability of very large amount of training data. Now, for most of the speech recognition system, it is comprised of 3 components: acoustic model, language model, and the decoder. Now, so here I'm going to talk mostly about acoustic modeling, which is essentially mapping the acoustic signal into the phonemes of the words. So our approach to speech recognition system is, particularly for acoustic modeling, is focused on using a bidirectional LSTM. No surprise, I think we have seen a great success of using the BLSTM. So the key idea is try to utilizing both the frames in the history as well as the frames in the future to generate the proper acoustic representation of signals. Now, even though the BLSTM yield better the recognition accuracy compared to the DNN, but it does have one shortcoming. The shortcoming is computational very high, and therefore it has a large latency. So to address this problem, we actually come up with a very simple scheme. That is, in order to reduce the computation, we simply just truncate the dependency, both for the historical frame as well as for the future frames. So the key idea would be taking the sequence of the frames and divide them into many chunks. Each chunk only comprised of small number of frames, and all the dependency will essentially being carried over within the frames of the same trunk without having to carry between the trunks. And that actually allowed us to dramatically improve the computational cost, leads to what we call latency control, the BLSTM. Okay, so if you compare the latency control BLSTM to the DN, we do actually find it is noticeably better performance. And this is the system that actually had been developed and deployed to our customer service department on March of 2016. Now, the next challenge we actually come is when we try to deploy our speech recognition system to the car. Now, people here, if you know that, most of the car has the embedding system, which unfortunately has a very limited memory as well as the computational capacity. So if you deploy a monster the model of the speech recognition system to a limited system of embedding, then you're going to encounter a lot of problems. One problem is that it's going to be, the latency is going to be very high, therefore it use a very bad user experience. So in order to further reduce the latency, what we do is that we actually simply combine multiple frames together to do the prediction for only every 3 frames in this case. And that actually allowed us to improve the computational cost by a factor of 3 and use a very desirable performance when we deploy that to the internet car by the end of 2016. Now, I understand that the work that we talk about for speech recognition here seems to be very engineering, but this is also the lesson I learned when I joined the industry. The simple is the better as long as it solves the problems. And I think that's a very good rule, even for the researchers, I think. Okay, so I would like to briefly talk about our efforts on so-called dependency passing. So for people not familiar with this area, the fundamental idea of dependency passing is to identify those head words from the sentence and furthermore build the relationship between the head words and words that modify the heads. Okay? So dependency passing has a lot of applications, for instance, sentiment analysis, information retrieval, extraction. Those are the places you do actually see a great application of dependency passing. Now, the recent years, people have, again, been successfully explored the deep learning technology for parsing. And I think one of the examples is a biofine attention parser. And so the idea basically is to estimate the score for all the possible arcs that it can build between the head words and the words that modify them. One limitation of the biofine attention parser is that the scoring function is only dependent locally between the words that you care about. And therefore, it loses the entire picture about the rest of the words within the same sentence. So our efforts is to building on the top of the existing neural network parser with additional adjustments by using the conditional random field. So by combining the global adjustment coming out of the conditional random field together with the power of neural network parser, we're able to yield better performance in this case. So for instance, if you look at this particular sentence, the retailers are increasingly cautious about expanding. The rents had remained steady or in some cases have been declined. So if you apply the bind-find parser to these cases, it will use some wrong dependency. For instance, it build a dependency between the quotient and the decline. And those mistakes can be avoided if you can introduce the condition random field object to bring up those global adjustments. Okay, then the next things I want to very briefly mention is the work we have done. We call it mimicked question answering. So people here probably all familiar with the question answering. So our goal here is not just building the question answering system, but also we like to generate a mimic figure that as if the figure is talking to the human subject to answer the questions. Right. So the basic pipeline is that someone was asking the question by the voice, and we have a speech recognition system transcribe those questions into the text, and the text will be fed into our QA system to identify the answer either by the FAQ or by machine reading technology. And the identified answer will then be fed into our TTS system, generate the acoustic signal. And then those acoustic signals will be fed into our graphic module to generate the lip and the facial expression motion for a figure. So in this particular, so in this system, now instead of system be able to provide answer to the user, you also get a feeling that there was an individual trying to address your question. And that really brings a better experience compared to the conventional QA system. Now, I think when I move to the next page, probably everybody would expect I will have a short demo of the system. Well, unfortunately, my answer is no, because I just tried out yesterday with our demo system. It does not work at all. So very, very sorry for the incapability of doing that, but I will promise you we're going to have our system online very soon, and hopefully you're going to see how it works. Okay, now the next things I would like to talk about is the combinatorial optimization using the deep learning technology. This probably is the subject may not be familiar to many of the people over here. So talking about the combinatorial optimization, I would like to give a first example, 3D bin packing problem. What is that? So I think the simple case is the follows. Now, if you are employee in some of working for the warehouse of some logistic company, actually one of your daily job is essentially taking the order, multiple items from the order, and try to pack them into the same box. Okay? Now, you often will encounter a decision that is how to choose the smallest box or the smallest number of boxes that is able to contain all the items from the same order. And that is a great instance of so-called 3D bin packing problem. Now, people may think this is a simple problem because this is a problem being taken care of by our many people in the warehouse. But turns out that this is very, very hard problem. It's an NP hard problem, and therefore there's no efficient solutions whatsoever at this point. As the results, in many cases, the problem is solved by applying different heuristics. And so, for instance, one of the heuristics would be you always put the largest item first in a box. The other heuristic would be you try to fit, finding the items that can give you the best fit with respect to existing layout of the box, and so on and so forth. So by working closely with our colleagues from China, we realized that one of the important things to reduce the number of boxes needed for packing is to actually identify right heuristic to be applied at a different scenario. So for instance, maybe at the very beginning of packing, you really want to put the largest item in a box. And later on, as you have more items in the box, you may want to find the best fit as the heuristics. So one of the key questions in terms of making the packing to be effective is to decide when and how to apply the different heuristic at different stage of this packing. Now, if you think about the problem, then you probably will realize this problem have large similarity to the problem being addressed by reinforced learning, right? Because the packing results is going to be affected by a sequence of decisions that you make. In particular, in our case, the decision is at each step, which heuristic you like to adopt to ensure the end results of the packing is going to be the optimal. Okay? Now, if you think about it in this way, then no surprise that you can apply the reinforced learning technology to learn the appropriate policy function for adapting the heuristic. So we have been working with our colleagues from the China on this for a couple of months, and with their help, and we work together to have some very interesting results. That is, by effectively using the deep learning technology, we actually be able to reduce the number of packing boxes by 5%. Now, you may think this number is not as great as you like to be, but think about how many boxes we have to consume on a daily basis for so many warehouses, and that accumulation number is not small at all. I cannot give you the exact number due to some policy, but I just want to let you know the economic impact of these results is not ignorable. Now, along the line, the other interesting optimization problem I'd like to mention is the banner design. So for people who have been working in the industry of advertisement, we probably all know that good design of the banner will have a great impact of user behavior. So often it's the case, the click-through rate is not going to be just reflected by the relevancy between the user versus the items, but also being affected by how appealing those banners are respect to the users. So the question is, can we do that automatically? Now, it's important to realize that the number of the banner or number of creative that have been generated by our e-commerce platform is tremendous. For instance, during our big shopping day, which is called Singles Day W11, we actually have to hire over thousands of designers to create millions of different banners in order to support the single day's efforts of advertisement. So if we can come up with an algorithm that is able to design the banner that is as appealing as the human experts, that can tremendously help the platform to cut the cost. Now, if you're looking at the problem of the banner design, you usually have a two phases. The very first phase is to select appropriate visual components based on the subject that you like to do the advertisement. Then the second phase is to figure out the appropriate layout of those visual components in the images so that the resulting creative or resulting banner will be appealing to target audience. Okay, so now again, as you can see, the end results of this banner design is again being affected by a sequence of decisions. Decision involving the selection of visual components and decision involving how to lay out those components in an appropriate and appealing way. And again, the reinforced learning technology is the one that really can help you to resolve those challenges and problems. So we have been working very close with the colleagues from our Alibaba department on the automatic banner design. Now, the other advantage of doing the banner design in an automatic way compared to manual efforts is that not only we can save a lot of efforts, but also we can generate personalized creative that can furthermore inspire users to interact with our system. And that is impossible to be done even though you hire tens of thousands of people to do that. Okay? And so last part of my talk, I would like to looking at our recent efforts on the model simplification. So as recently we have seen, the people have made a lot of efforts to make our network to be very deep. So one example is that if you look at the recent competition of ImageNet, people actually have designed a neural network with over 1,000 layers. It's just unbelievable. Now, those deep neural networks, on one hand, do bring a tremendous performance, but on the other hand, also cause a lot of headaches. It is computationally expensive, requires a lot of memory, involves billions of different parameters. Okay? So there's been a lot of efforts try to make those complicated models simple. And one of the efforts is to do the Lowbit quantization. The simple way to do the Lowbit quantization would be you taking all the numerical weight you obtain for the deep neural network and try to quantize them by a small number of bits. The simplest way would be you take any numerical number and map it to be +1 if it's a positive number and a -1 if it's a negative number, and totally ignore its numerical values. Apparently, this kind of approach usually gives you a very limited performance. Now, the other approach people have done in terms of Lowbit quantization is injecting the compression, the quantization component into the network. So you can have a step function that adding to the network such that it always compresses the numerical number into the +1 and -1. But unfortunately, in order to carry out all this gradient computation, you actually have to approximate those step functions as a function with a slope, which again use suboptimal performance. So our efforts towards Lowbit quantization is quite different from most approach. We basically take so-called ADMM theory as our guidance. ADMM stands for alternating direction method of multiplier. So the key idea is that we're going to maintain two sequences of solutions. One is a continuous and the other one is a discrete. And then we utilize the theory of ADM to enforce the consensus between these two sets of solutions by introducing so-called modified Lagrangians. Now, unfortunately, by using this theory itself, even though it gives you a good performance when you're looking at large number of bits, but when you get into the territory of very small number of bits, it usually gives you a very poor performance. And we actually addressing this challenge by using so-called extra gradient approach. This is a very old theory invented in like 1970 and actually gave a very good performance in our practice. And so the basic idea is that we're going to leverage the gradient information from the discrete solution to guide the search of the solution in the continuous space. That turns out works very well in empirical. So as you can see, the red curve is directly using the ADMM, while the blue curve is the results if you're using the extra gradient combined with the ADM. And we also prove why it used a better convergency compared to the standard gradient approach. Okay, so we have done quite extensive evaluation about this approach, and this is just a very small sample of our evaluation. So this is evaluation carried over in ImageNet dataset using the residual network 50 layers. So if you run this residual network 50 layer with full precision, you're going to get like 75% accuracy for the top one and then 92% accuracy for top 5. Now, if you enforce yourself, only use 1 bit as the way to represent each of weight. Using our approach, you're able to get 68% accuracy for top 1 and then 99% accuracy for top 5. Now, the best compare in the market, we find that only use 63 accuracy for top 1, 85% accuracy for the top 5. So as you can see, having introduction of ADM technology together with the extra gradient does actually give us a lot of advantage in the final performance. And we also have evaluated the results in the detection task by using the Pascal VOC challenge dataset 2014. Okay, now last part I would like to talk about this probably slightly philosophical question, that is deep versus shallow, right? So as I said before, there's been a clear trend in many of the efforts that when people try to catch in the sophisticated function, they always look at the efforts of making the network to be very, very deep. Now, this is not just actually practice. There's also been a lot of theoretical study verifying that deep network indeed has a tremendous representation power compared to the shadow network. For instance, if you want to model very local function, you can show that if you allow yourself to use the deep network, then you can have very compact representation. However, if you restrict yourself to the shadow network with a layer 1 or 2, then the size of network of shadow network tends to grow up exponentially. So all this evidence seems to indicate that really there's no hope whatsoever by simply just using the shadow network. But I think all this argument seems to have one missing point. This missing point is that all this study assume that activation function being used by the neural network is predefined and the data independent. So the question is, what if I can try to twist the activity function in a way that allowed me to express very sophisticated function by using a small number of layers? Is that possible? The answer actually is yes. So it turns out in 1980, mathematician Adam Pincus and his colleagues actually proved this wonderful theorem. I basically tell you that for any bounded continuous function, there exists a sigma type activation function to be such that every continuous bounded function can be approximated with arbitrary accuracy by a network with only 2 hidden layers. And the most important, the width of the network is bounded by the dimension. So roughly the size is 4 times d plus 3. D is the input dimension. So as I plot over here, turns out if you can smartly twisting your activation function with respect to the data you have seen, you actually can represent any continuous bounded function with arbitrary accuracy by using a network with only 2 layers. Okay, now apparently you are saying, look, in this case, I really have to deal with not only learning of those weights, but also I have to learn the activation function. Is that easy job or not? Well, turns out one advantage of learning activation function is that all the activation function is univariate. And learning a univariate function in a parametric way is extremely well established in the community, right? So the most well-known approach is spline, for instance. Okay, so all these actually are good news, but turns out I think many things remains unknown and open. So one thing is we call sample complexity, right? So yes, we can try to learn both the weights as well as activation function. But how many sample size we need to accomplish this learning task? Is it possible that we really need too many examples to learn univariate functions? Now remember that turns out the learning complexity or sample complexity is not necessarily just depends on the input dimension of the function. It also depends on the complexity function. For instance, we all know that for periodic function like sine, its VC dimension is unbounded, right? Meaning that you're going to have many, many training examples before you can pin down that periodic functions. So this is the first question. The second question is again about learning, optimization, because we now know in order to accomplish this task, you not only have to learn those ways, you actually have to twisting the activation function. How to do that, right? Is it possible that you can land your results with the local optimal or even the global optimal, right? I think all these are the questions without the answer. Now, nevertheless, our team had been working very extensively on this direction. We really think that it's possible to deliver a very shallow network that has the same representation power with the deep network as long as we can twisting the activation function in the appropriate way. So this is pretty much conclude my talk. So I think my take-home message, I think, at least my experience with deep learning at Alibaba is that, yes, indeed, on one hand, I do have to admit, regardless how reluctant I am, that deep learning did bring tremendous performance. You cannot deny it. It's just a fact. But I think, on the other hand, we should also question the foundation, right? Because there are many, many interesting questions remains to be resolved. Optimization, how can we do the optimization effectively? How can we guarantee the solution is even local optimal? Is it possible to come up with a shadow network that will do the same job as the deep network? And I really believe that with the help of the industry as well as the efforts from the academia, we should be able to come up with some interesting and exciting answers to those questions. And I strongly believe the answer to those fundamental questions will really bring the technology as well as the application to the very next stage. Thank you very much for your time.
So thank you. So now we can just have one very short question. Please use the microphone if you have a question. Any people? So hopefully, I just have one question. I hope to ask. Previously, you are theoretical, mostly theoretical researcher. Now, when you go to engineering, you said that very smart engineering tricks might be more effective, simple yet effective. Do you have encountered any obstacle in this transfer?
Oh, okay. I think for the early days when I was in Alibaba, I was really not comfortable with the engineering tricks. I always thought anything without elegancy of proof the bounds is totally useless. I mean, you may actually laugh at this attitude, but that's actually true for most efforts I've done at very age. So then actually I realized that particularly for the territory like deep learning, we have so many things that we don't know. So indeed, theoreticians should work closely with empirical people, because many of the discovery that indeed may open a new insight to the problem coming from the empirical side. So for instance, I was mentioned the extra gradient idea, and this is actually was first invented by our engineering team. I have no idea how to solve the problem at the beginning. When they tell me the solution, I realize there's a very close connection between the engineering efforts versus the underlying theory called the extra gradient. And that actually brings the theory to the table. So again, and my feeling is that if we can do the job right, engineering people actually will bring a tremendous, exciting insight to the theoretician, which essentially allowed us to open the door to the amazed world.
Okay. Because of time, we have to post all the questions offline. Let's thank Dr. Jin for the wonderful talk.
Thank you.
Thank you very much. So this is the end of our invited talk session. We'll start in 3 o'clock. Thank you very much.